Hello, class. Welcome to lecture 8.2. We'll be doing the constrained optimization using the Lagrange method. And then afterwards, I will show you how there's a closely related problem called the dual problem to utility maximization, and that's expenditure minimization. And so we might as well just hop right into this bad boy. The motivation for this is there's actually multiple ways for solving constrained optimization problems or utility maximization problems that we've worked on so far. So just like substitution, it's going to convert a constrained optimization problem to an unconstrained problem. So we can use those methods. And this works for like a broader class of problems. So like if you have a really hard problem, then it might be worth looking at how Lagrange applies to it. Put a note here, like if you're going to go to economics graduate school, you're going to use this method because it's better for just really kind of complicated functions that would be hard to keep track of if you do substitution. I guess like kind of the drawback you can think about for now is there's like it's unfamiliar to you probably, whereas substitution is pretty straightforward. So there are some places you can get slipped up using the Lagrange method, but it's really generally useful, and you can kind of take some L's with Lagrange. There are more potential dubs from using the Lagrange multiplier. So anyway, basically all I'm saying with all of this text is that there's a different way to find this orange point than I've showed you so far, and I'm going to take you through an example in this class. So the Lagrangian function is what we need to set up, which is this fancy L. And the Lagrangian function is literally only three ingredients. The first one is the objective function, so that's the utility you're trying to maximize. The second one is the constraint, what you're optimizing subject to. And so in our utility maximization example, this is the budget constraint. And then the third ingredient, which you haven't seen so far, is this Lagrangian multiplier, lambda. And I don't want to get too in-depth about the Lagrange multiplier because it's not crucial to finding the optimal bundle. But for now, you can think of it as it's interpreted as the marginal utility from a small relaxation of the constraint. So if you get a little bit more income, what would your marginal utility be? And like I said, we're just trying to get Q1 star and Q2 star out of this. And you can talk to me if you're more curious about lambda. I'd be happy to talk about it more with you. And so kind of all you need to do is plug in the objective function, but for the constraint, you need to do kind of something else. You need to rearrange it so that it's equal to 0. So normally you have income equals price of 1 times quantity of 1 plus price of 2 times quantity of 2. That is, you spend all your money on either good 1 or good 2. All I did was subtract P1, Q1, and minus P2, Q2 from both sides so that the entire constraint is equal to 0. Income minus P1, Q1. And then you can you need to plug this Y minus P1 minus P2 times Q2 into where the constraint goes. So it's just a little bit of algebra on the front end, and it'll help you with more difficult problems. So this is it, right? Like I haven't specified a utility function yet, so I just have some function of Q1 and Q2 here as the objective function. Our second ingredient, lambda, the Lagrange multiplier is just right here. And then our constraint is here. So we're spending all of our money, Y, on either good 1 or good 2. And that's really it. That's the Lagrangian. And that's what we need to set up to work with. Just to make it a little bit more concrete, I like say we could pick our utility function here, what we're trying to maximize, how we translate consumption of good 1 and good 2 into happiness or well-being or satisfaction, utility. And so this is just that. So we have the natural log of Q1 times Q2 as our first ingredient, our second ingredient, lambda, and our third ingredient is a constraint. And so this is pretty straightforward. But Ben, like, what do you need to do with this bad boy? So here's just some more formality real quick. We're going to choose Q1, Q2, and lambda, which is kind of hard to think about. I want you to think of lambda as a choice variable too for now, even though we're not really choosing it. And so our choice variables are Q1, Q2, and lambda, subject to income and prices. And so now here's like kind of our formal definition of our Lagrangian problem. Let's get into an example. So, or actually not quite yet. To solve this thing, you just need to differentiate the Lagrangian with respect to each choice variable, aka you need to find first order conditions. The choice variables are Q1, Q2, and lambda, and you need DL dQ1, DL dQ2, and DL d lambda. After you have those, you set each one of those partial derivatives equal to 0, so you can find the maxima or the minima of the functions. And we're looking for the maxima of constrained utility. And we're just, after having all of those, we just need to be clever enough with algebra to solve for Q1, Q2, and lambda. And it's just 3 equations with 3 unknowns. So you should be able to do that. There's no really correct, technically, way to get there, but an easiest order usually exists for how to do things. And typically you need to practice a lot of problems to have an idea of what the easiest way is to do Lagrangian. So last class, 8.1, I solved number 23 on page 95 using the substitution method. So you've seen that. I want to solve the exact same problem now, but using the Lagrangian method, so you can see that as well too. So let's say we have the same things from the last problem. So our utility is equal 10 times rib squared times chicken. And our budget constraint is income equals the price of ribs times how much ribs we eat plus the price of chicken times how much chicken we eat. And the price of ribs is 10, the price of chicken is 5, and the income is 90. And so y equals 90, 5 is price of chicken, and 10 is price of ribs. And it's really not too hard to see that this is our Lagrangian, right? So ingredient 1 is our objective function, which we're trying to maximize our utility right here. Our second ingredient is this lambda, or the Lagrangian multiplier, times our budget constraint, which is just 90 minus 5c minus 10r. And so, yeah, we've got our problem set up. And now we need to find the extreme points of the Lagrangian. So we take the derivative with respect to R, C, ribs, chicken, and lambda. And then we'll set them equal to 0 and solve. And so I went ahead and took the partial derivatives of this function for you so that you can see what our kind of our first order conditions are. And so here's our 3 equations. And we have R, C, and lambda as our 3 variables that we need to solve for. And so, like I've been saying all along, our 3 ingredients to Lagrangian. And now what we need to do is solve for R, C, and lambda after setting them all equal to 0. Again, define the extreme points of the function. And, you know, this is just 3 unknowns, 3 equations, right? You got this. This is easy. This is algebra. So I'm going to start with eliminating lambda from the system. And so how I can do that is I can say from 1, rearranging this to solve for lambda, I know that lambda equals 2rc. And from our second equation, we know that lambda equals 2r squared. And so by definition, lambda must equal lambda. And so we know that lambda equals 2rc, and we know that lambda equals 2r squared. And so we can just set them equal to each other. And then we have a way to express r or c only in terms of the other variable. And so that's what I do next. I solve for c and from this equation, and I get c equals r. Easy. I plug this into equation 3. So I've got 90 minus 5r minus 10r, or 90 minus 15r, or 15r equals 90, or r equals 6. So I've got r equals 6 now, and I can plug r back into this and solve, and I can get c equals 6. And so if you recall from our last lecture, you'll remember that 6, 6 was the optimal bundle using substitution also. So both work and find the same answer. And I'll just point out you could solve for lambda 2 if you wanted. That would be, you can interpret that as your additional utility from a small relaxation of the constraint. I'm not going to do that now because I wanted to find the optimal bundle was the instructions, but if you're interested, this is not too hard given that we already have R and C in the equations for lambda. So feel free to do that yourself. So that's a really interesting alternative way to solve constrained optimization problems. And I encourage you to take a look and try to figure it out because it's a nice way to solve these problems. So so far we've done substitution and the Lagrange method, which I just showed you. And both of those methods are meant to help you maximize your utility, that is, find the highest indifference curve possible, subject to the amount of money that you have, this budget constraint. So it looks for this orange, both of those methods looks for this orange point right here. And I want to kind of walk through exactly kind of what that looks like. You can kind of interpret this utility maximizing as, for my budget and prices, what is the highest indifference curve possible? And so it kind of has this fixed gray budget constraint here, with which you have to try to get to the highest blue indifference curve. And so if we had this budget constraint, which I'm calling BC, and this indifference curve of utility equals 1 here, we could get utility equals 1 from this budget constraint because all these bundles of goods are possible given our budget constraint. However, we know that there is a higher utility possible than utility equals 1. And so what about utility equals 5,000? Well, this utility is unobtainable because these bundles of goods aren't on or within the budget constraint. That is, given our income and prices, we can't afford any bundle of goods on this indifference curve. And so the highest obtainable utility, which I'm calling U equals 4,187, just to kind of like make a point that utility is ordinal here, is that this utility, this indifference curve, needs to be tangent to the budget constraint, which means their slopes are equal, which means that the slope on an indifference curve is the marginal rate of substitution, and the slope on the budget constraint we're calling the marginal rate of transformation. And so if those things are equal, then we say we have the optimal point, and Q1 star equals Q2 star. You guys are probably pretty familiar with that at this point. But there's another way to think about it, is what is the minimal amount of expenditure I have to spend to get to a target utility level? And this is named kind of the dual problem. And so let's say we just have this target utility level of U equals 4,187. We want to know what's the minimum amount I can spend to get utility equals 4,187. And so we say, well, with a budget constraint where our income is equal to 5, this is our budget constraint, and we can see that there are this utility we get to is neither inside nor touching the budget constraint, and so the bundles of goods that give this level of utility are unaffordable, and we say I'm not spending enough at income equals 5 to be able to reach a target utility level of 4,187. And so what we do is we say, well, what if we had our budget constraint for an income of 15? We'd say, well, yeah, we can afford this bundle of goods or this bundle of goods, and get a utility of 4,187. But we could also reach this same level of utility for a lower amount of expenditure. And so just like with the utility maximization, the minimal expenditure for a target utility is where the expenditure is exactly tangent to the utility curve on this budget constraint of income equals 10. And so right here we know is our optimal bundle, which you would find the same exact answer for the same exact problem, whether you did it via expenditure minimization or utility maximization, because of the dual of one another. And the optimal point condition is the exact same, so it's where the marginal rate of substitution equals the marginal rate of transformation. You might be asking me, like, why do I care about expenditure minimization? And there's kind of two reasons. The first one is like a practical reason. If you're really interested in economics and going on and doing this, then oftentimes utility is unobservable. There is no data on utility. There's data on like subjective happiness, but that's different from like actually a number of how happy you are. And then the other one is that we will be using this kind of solution method um, in further units in this class when we talk about firms. And so they're important. And basically what I want you to take away is that we have this constrained optimization, which is at the core of economic theory. We're going to derive a lot of economic predictions using just this setup right here. And this Lagrangian setup that I showed you today can be used to make kind of the mathematics and the algebra easier, as long as you understand the calculus of what's going on. And then just that expenditure minimization will give you the same optimality results as the utility maximization problem. So it's pretty important to know that as well. And that's everything for today. Hope you enjoyed, and I hope you have a great weekend. And I will talk with you next week.